Have you ever wondered how a computer can look at millions of pixels and somehow say, that's a cat? It doesn't have eyes, it doesn't understand images the way we do. Yet CNNs power everything from face recognition to self-driving cars. In the next few minutes, we are going to break down exactly how a CNN transforms raw pixels into intelligent predictions. Let's dive in. Before we zoom into individual components, let's look at the entire pipeline. A CNN follows a surprisingly structured process. An image enters the network as raw pixel values. Those pixels pass through convolutional layers that extract patterns. Pooling layers compress information. Feature maps become increasingly abstract as we go deeper. Eventually, everything is flattened, passed through dense layers, and converted into probabilities. Think of this architecture as a visual understanding pipeline. Every stage answers a slightly more sophisticated question than the previous one. The first thing to understand is that a CNN doesn't see images the way human does. When we look at a cat, we instantly recognize ears, whiskers, and eyes. A CNN sees none of that. It only receives a giant matrix of numbers. For grayscale images, every pixel is represented by a value between 0 and 255. 0 means black, 255 means white. For color images, things become even larger because every pixel contains three channels: red, green, and blue. A typical 224 by 224 RGB image contains more than 150,000 numerical values. At this stage, there is absolutely no understanding of objects, just numbers. The CNN's entire job is to discover meaning hidden inside those numbers. This is where the magic begins. The convolutional operation uses a small matrix called a kernel or filter. Imagine taking a tiny 3 by 3 window and sliding it across the image. At every position, the network multiplies the filter values with the corresponding pixel values and sum everything together. This operation is called a dot product. The output tells us how strongly a specific pattern exists in that region. Different filters learn to detect different visual structures. Some become edge detectors, some detect textures, others respond to gradients or orientations. And here's the important part. Nobody manually programs these filters. The network learns them automatically during training. Convolution is essentially pattern matching happening across the entire image. Every filter creates its own output image called a feature map. Think of a feature map as a heat map showing where a specific pattern was detected. Bright regions indicate strong activations. Dark regions indicate weak activations. One filter might highlight edges, another might highlight vertical lines, another might respond to curves, and another might activate around corners. After convolution, a ReLU activation function removes negative values and keeps only useful signals. In modern CNNs, dozens or even hundreds of filters operate simultaneously. This allows the network to build a rich representation of the image from many different perspectives. Now that we have detected patterns, we need to make the representation more efficient. That's where max pooling comes in. Pooling looks at a small region, often 2 by 2, and keeps only the largest value. Instead of storing every detail, the network preserves only the strongest signal. For example, a 4 by 4 feature map can become a 2 by 2 feature map after pooling. That's a huge reduction in data. Why is this useful? It reduces computation, it reduces memory usage, it helps preventing overfitting, and most importantly, it makes the network less sensitive to small shifts in object position. The network learns what exists, not exactly where every pixel exists. This is arguably the most fascinating part of CNNs. As layers stack on top of each other, features become increasingly sophisticated. The first layers detect simple edges. Those edges combine into corners and curves. Corners and curves combine into shapes. Shapes combine into object parts. Object parts combine into complete objects. For facial recognition, early layers may detect lines. Middle layers may detect eyes or nose. Deeper layers may understand the complete face. This hierarchy emerges naturally during training. No engineer explicitly tells the network what an eye looks like. The network discovers it because it helps reduce prediction errors. That's one of the most powerful ideas in deep learning. After several rounds of convolution and pooling, the network has extracted a huge collection of learned features. Now it needs to make a decision. The first step is flattening. All feature maps are converted from a 3D structure into a long 1D vector. This vector becomes the input to fully connected layers. In these layers, every neuron connects to every neuron in the next layer. These dense layers learn relationships between features. For example, maybe whiskers plus triangular ears plus certain textures strongly indicate a cat. The dense layer learns these combinations and converts features into decisions. At this point, the network produces raw scores called logits. These scores aren't probabilities yet. To convert them into meaningful probabilities, we use the softmax function. Softmax transforms the scores so that all outputs add up to 100%. In our example, cat gets 92%, dog gets 5%, horse gets 2%, and car gets 1%. The class with the highest probability becomes the final prediction. So the CNN confidently predicts that the image contains a cat. Everything from raw pixels to this prediction happened through learned mathematical transformations. But how did the network learn all of this? The answer is backpropagation. Initially, every filter contains random values. The network makes terrible predictions, then training begins. First, the image moves forward through the network. Next, the prediction is compared with the correct answer. The difference becomes the propagation calculates how much every weight contributed to that error. Using gradients, the optimizer adjusts those weights slightly. Then the process repeats again and again, millions of times. Over time, random filters transform into edge detectors, texture analyzers, shape recognizers, and eventually powerful object detectors. This learning process is what turns a CNN from random noise into an expert visual system. Let's quickly recap. A CNN starts with raw pixels, convolution, discover patterns. Feature maps highlight important structures. Pooling compresses information. Deep layers build a hierarchy from edges to complete objects. Dense layers combine learned features. Softmax converts scores into probabilities. And backpropagation teaches the entire system how to improve. The incredible thing is that CNNs aren't programmed to recognize cats, cars, or faces. They learn a visual language directly from data. And that simple idea has transformed computer vision forever. If you enjoyed this deep dive and want more videos breaking down AI concepts visually and intuitively, make sure to subscribe. Thanks for watching and I'll see you in the next one.